In the last section of this chapter, and really the last section of all of the equilibrium chapters, although equilibrium constants will come up again in later chapters, the topic is KSP, or product solubility constant. So essentially what we're looking at here is insoluble solids. So here's an example of AgCl. And if you remember back to your solubility rules, chlorides are generally soluble, but silver is an exception. So silver chloride is not very soluble in water. And in fact, in General Chemistry 1, we said it's insoluble. But it turns out that's not 100% true. Although it's mostly insoluble, it's not very soluble, it is slightly soluble. So when you first start by adding, this is silver chloride, into a beaker of water, what you end up with is no silver ions or chloride ions in solution. But if you wait a little bit of time, you'll get some silver and chloride ions in solution. And you end up with this dynamic equilibrium where some of the silver chloride is dissolving and forming Ag plus aqueous and Cl minus aqueous, and some of the silver chloride is recombining into a solid, and you have this dynamic equilibrium happening. We could write a Kc expression for this. The Kc is products over reactants, Ag plus times Cl minus over AgCl. But what you notice here is it's not over anything. Why not? Because AgCl is a solid. We only put aqueous and gases into our KSP expressions, or our Kc expressions, or we don't put liquids and solids into our Kc expressions. Well, this Kc has a special, abbreviation, if you will, the KSP, the product solubility constant. And it's the exact same mathematical value. We just, instead of Kc, we call it KSP, just like we did with Ka and Kb. They were just special cases. So KSP is yet another special case. So where is this useful for having these insoluble solids? Well, wastewater treatment is one area where this is useful. And there are many things that are treated from wastewater, but one of them is heavy metals. And heavy metals are precipitated as hydroxides and or sulfides and or carbonates. And these different compounds precipitate out. And since they aren't very soluble, sulfides, carbonates, and hydroxides are generally insoluble, back from the solubility rules in General Chemistry 1, these compounds then precipitate, and therefore the treated water doesn't contain the heavy metals like lead and mercury and things like that, which precipitate out as these different compounds. Then they can be filtered, or whatever the case may be, and removed from the wastewater. Another example where solubility product constant is used is in the medical field with barium sulfate. Patients are given barium sulfate if they're getting a scan to see if they have an ulcer or something. Okay, I'm not that knowledgeable about medical things, but that's not what we're looking at here. First of all, it probably isn't to many people, but it's quite remarkable that someone's drinking barium. Okay, this would be like drinking lead. It's heavy metal is probably not the best idea. However, barium is very, very insoluble in water. So there's very little barium ions in solution, and therefore they've deemed that it's safe enough to drink. So barium sulfate can be ingested into the system. And you may be asking yourself, well, why use barium in the first place? Well, heavy metals tend to be better at absorbing X-rays. And in this case, they're taking a CAT scan or an X-ray or whatever they're taking. And basically, this allows them to visualize this because the barium is able to absorb it. But it is also not soluble enough that so it doesn't actually cause any health problems. So this is how barium sulfate works. Generally speaking, the smaller the KSP value, in the case of barium sulfate, it's 1.1 times 10 to the minus 10, the less soluble the compound is. But as you're going to see in a few minutes, it does depend on stoichiometry. So this isn't an absolute statement. All right. You can't say that if this has 1.1 times 10 to the minus 10 and something else has, 9 times 10 to the minus 9, that this is less soluble. But generally speaking, if the KSPs are smaller, you're going to have less solubility. let's take a look at a few examples of this. The question asks, write the balanced chemical equation for the dissociation of the following ionic compounds, and then write the KSP expression. So here we have CaOH2, calcium hydroxide. Hydroxides are generally insoluble, so we can make that solid. I need to put the camera up, though, in order for you to be able to see what I'm doing. So we could take CaOH2 as a solid. This is going to be in equilibrium with Ca, which is 2+, it's a 2A metal, aqueous, and OH minus, aqueous. Note that because it's CaOH2, we're going to get 2 OH minus. And if we want to write the KSP expression for this, the KSP is going to be equal to the concentration of Ca2+ times the concentration of OH minus squared. Notice that we do not put the CaOH2 on the bottom because it's products over reactants, but we don't put the reactant on the bottom because it's a solid. So we don't put liquids and solids in our KSP expression, or we only put things that are aqueous and gases in our KSP expression. Let's look at magnesium carbonate. This is the stuff that gymnasts put on their hands, that white chalky stuff. So magnesium carbonate, solid, is in equilibrium with another 2A metal, Mg2+, aqueous, and CO3, 2-, polyatomic ion carbonate, aqueous. What's the KSP here? Well, the KSP here is the concentration of Mg2+ times the concentration of CO3, 2-. So in this question, we're simply looking at writing the KSP expressions and the reactions that are occurring for this solubility. In the next question, we actually want to put some numbers into this. So we have here, what is the molar solubility of each of the following? All right, so the molar solubility is essentially, what will the molarity of this be in solution? Okay, so we need to be able to find the molar solubility of these things. So here we have CaOH2, and the KSP of this is looked up as 4.68 times 10 to the minus 6. You can actually find these things on the internet if you need them. So we have the reaction we just wrote and the KSP expression that we just wrote. And now we're going to use an icebox, just like we did before. So when we first dissolve this solid, just like in the picture of AgCl a few slides ago, we start with just this. So the initial concentration of Ca2+ and OH minus are both 0. In this case, we don't know how much we're going to get. We're going to get X of Ca2+. But notice the stoichiometry. If we get X of this, we must get 2X of this. Why? Because for every one of these we get 2 of these, or said another way, if we get X of this, we get 2X of this. At equilibrium, we have X of this and 2X of this. So now we can write the KSP expression, which was actually given to us, so I guess we don't need to rewrite it, but Ca2+ OH minus squared. Okay, I forgot, it wasn't actually given to us either. We did it in the previous question. So we have the KSP value. We looked that up. You can find them on the internet, as I mentioned. And now we have X and 2X. So we take the KSP value, which is 4.68 times 10 to the minus 6 equals X times 2X squared. 2X squared is 4X squared. So we get 4.68 times 10 to the minus 6 equals X times 4X squared. We have to square both the 2 and the X. So we get 4X squared. And when I'm going to flip it around, 4X cubed equals 4.68 times 10 to the minus 6. Divide both sides by 4. And we get X cubed equals 1.17 times 10 to the minus 6. We now take the cube root of this and the cube root of this, and we get that X is equal to 0.0105 molar. What this means is the concentration of calcium hydroxide in solution would be 0.0105 molar. It would be the same as the concentration of Ca2 plus, or the same as X, because one of these gives one of these. You would not want to double it for a hydroxide because one of these gives two of these. So therefore, the concentration or molarity is this one, and we call that molarity the molar solubility. Let's look at the next example. Okay, the next example asks us about magnesium carbonate, and we already had written the KSP expression for that one. In this case, the initial concentration of magnesium and carbonate both start off as 0, just like the other one. We gain X of magnesium and X of carbonate. Notice here that they're 1-to-1, so we get X and X. At equilibrium, we have X of this, and at equilibrium, we have X of this. We have the KSP expression, and we have the KSP. So plugging in 2.06 times 10 to the minus 13 equals X times X, or X squared. X squared equals 2.06 times 10 to the minus 13. We take the square root, we take the square root. X equals 4.54 times 10 to the minus 7 molar. So the concentration of this one would be 4.54 times 10 to the minus 7 molar. So this is applying mathematical operations or actual numbers to these types of problems. There's one last thing that we need to do in these 3 equilibrium chapters, and this is the common ion effect. Okay? The common ion effect is what happens to the solubility if we add a common ion. And this goes back to Le Chatelier's principle, but in the next examples, there's 2 of them, we will actually put some numbers to this as well. So here we have AgCl, and it's in equilibrium with Ag plus and Cl minus. We showed this earlier. What would happen if we use the solution of NaCl? Well, NaCl would produce Cl minus, and that means we would have more product Cl minus. Well, what is the reaction's only way to deal with this extra Cl minus, or what is the reaction's only way to get rid of Cl minus? It's to shift in the opposite direction back towards AgCl. Said another way, AgCl is less soluble in a solution of NaCl because it has a common ion, chloride. Remember, this is called the common ion effect. What about barium sulfate? Well, barium sulfate, what about its solubility in sodium sulfate? Sodium sulfate is going to be a source of sulfate ions. If you increase the concentration of sulfate, it shifts the reaction to the left towards barium sulfate, making barium sulfate less soluble. So generally speaking, if you have a common ion, okay, that common ion is going to make the overall compound less soluble. Let's take a look at a couple mathematical examples, and as usual, I'm going to switch over to the camera in order to do that. It says, calculate the molar solubility of MgCO3 in 0.1 molar Na2CO3. If you remember from the previous example, we found that the molar solubility of MgCO3 in just water is 4.54 times 10 to the minus 7 molar. Now, if you remember what we talked about just a second ago, we said that it should be less soluble in a common ion. In this case, the common ion is carbonate. So if we add carbonate to the solution, will this become more or less soluble? Well, we think less soluble, but let's do the math and figure it out. Okay, we are again given the KSP of magnesium carbonate. Now let's look at initial change and equilibrium. In this case, the initial concentration of Mg2 plus is 0. But the initial concentration of carbonate is not 0. It's 0.1 molar because it's going to be the same as the concentration of carbonate. Sodium carbonate is soluble, so it's going to dissolve into Na plus aqueous plus CO3 2 minus aqueous. Said another way, if we have, and we should have a 2 here, if we have 0.1 molar this, we have 0.1 molar this because sodium carbonate and carbonate are 1 to 1. So the initial concentration of carbonate is not 0, it's 0.100 molar. Change. We are again going to add X of this, we don't know how much, and we are going to add X of this. And what we end up with at equilibrium is X of magnesium 2 plus and 0.100 plus X for carbonate. Now, we're going to do the exact same thing that we've done every other time. We are going to ignore this X so that we don't have to use the quadratic equation. So we're going to put 100 here. We're going to assume that this is less than 5% of 0.1. Again, I've only chosen examples where that is true. Okay, you could choose examples where it isn't, but this isn't one of them. All right, so now we have our KSP expression, we have our KSP, and we have our equilibrium concentrations. So let's plug in. So KSP is 2.06 times 10 to the minus 13 equals X times 0.100. Note, we're again dropping this X, so we're just doing X times 0.0100. Divide by 0.100, divide by 0.100, and we find that X is equal to 2.06 times 10 to the minus 12. This concentration is less than this concentration, so adding a common ion, in this case carbonate, made magnesium carbonate less soluble, about 5 orders of magnitude less soluble. All right, let's see about MgCl2. All right, in this case, what happens to MgCl2? Well, MgCl2 is going to dissolve, if it's a solid, to form Mg2 plus aqueous and 2Cl minus aqueous. In this case, you can see that the MgCl2 actually increases the concentration of Mg2 plus. The Cl minus is going to have no effect because it doesn't have a common ion in this case. So when we add this, the initial concentration of Mg2 plus is the same as MgCl because we have a MgCl2 because we have a 1-to-1 stoichiometry. So this is going to be 0.225 molar. The initial concentration of carbonate in this example is 0 because this doesn't have any carbonate in it. How much of this are we going to gain? X. How much of this are we going to gain? X. We're going to drop the X again, so this at equilibrium will be 0.225, and this will be X. Plugging into the KSP expression. KSP, which is still 2.06 times 10 to the minus 13, equals 0.225x. Divide by 0.225, and we find that X, or the molar solubility, is equal to 9.16 times 10 to the minus 13 molar, which is certainly less soluble when we have this common ion than it was without the common ion, which was the previous question. So you can see that the common ion effect holds true from a Le Chatelier's principle standpoint. If you add magnesium, it's going to drive the reaction towards the reactants, i.e. making this less soluble. And it also holds true from a mathematical perspective. As we calculate the molar solubility, you can see that this molar solubility is much higher, 10 to the minus 7, as opposed to this one, which is much smaller, 10 to the minus 13. So there's been a lot of equilibrium in the past 3 chapters, and it kind of builds on itself, and the titration stuff and to some extent the buffer stuff in this chapter are quite complex. I think you get a little bit of a break with the KSP. It's not too terrible, but this stuff definitely takes practice. So please make sure to practice these examples.